Okay, thank you, Miss Fabi. Please let me remind for all the participants to to mute the the microphone, please, so we can start the sessions in a minute. So, Bismillahirrahmanirrahim. In the name of Allah, the most gracious, the most merciful, all the praises and thanks to be Allah and peace upon our Prophet Muhammad Sallallahu Alaihi Wasallam. Assalamualaikum warahmatullahi wabarakatuh. Good day, ladies and gentlemen. The honorable all invited speakers and the honorable all participants of this conference in room D. Welcome to the third International Conference on Chemistry, Chemical Process and Engineering IC3PE 2020 in webinar platform. My name is Sri Agustina, and it's my honor to be the moderator for the invited speaker sessions in room D. So in a short while, we will start our sessions, which will be break into 2 sessions and last for about 40 minutes. So in the first sessions, we will have Dr. Eko Adi Prasetyanto and Dr. Suresh Sagadevan as our invited speaker. Each speaker will have 15 minutes to share their presentations. Then we will continue to the question and answer sessions for 10 minutes. So all the participants can deliver their questions to each speakers by typing your question through the chat windows. So please type your name, institution, and your questions in the chat panel window, and I will read your questions later. So first of all, may I briefly introduce to you our first speaker, Dr. Eko Adi Prasetyanto from Department of Pharmacy, School of Medicine and Health Science at Atmajaya Catholic University of Indonesia. Dr. Eko is specialized in the nanomaterials for various applications such as drug delivery, biosensor, and bioimplant. He has published 59 research articles in high-impact journal as co-author and corresponding author, and obtained 10 patents filed. He received his PhD degree from Inha University Korea in 2010, and he's currently a vice rector for research and collaborations in Atmajaya Catholic University. And today, Dr. Eko will be sharing with us his expert opinion on the understanding living cell interactions with silica nanomaterials. So without further ado, please give your full attention to Dr. Eko Adi Prasetyanto. Dr. Eko, the time is yours for the next 15 minutes.
Thank you, moderator. I share my screen, and is it? Can you see it?
Yes, we can see it.
Okay, perfect. Thank you very much. Thank you to the organizing committee for the invitation. This afternoon, I would like to share our small study, how we try to understand the interaction between material, nanomaterial, especially silica nanomaterials with the living cells. So why we try to do this one? Because in the last decade, nanomedicine, the application of nanotechnology to medicine, widely done in the many research center. And then what's nanomedicine? In the nanomedicine, they use a submicrometer size tool to diagnose, prevention, and treatment of the disease. So they use a lot of type of materials such as gold nanoparticles, silver nanoparticle, various metal oxide nanoparticles, also silica nanoparticles. In my case, I would like to share how we use the silica-based materials. Why? Because we can easily tune the silica, especially mesoporous silica, to have many different parameters, such as we can easily tune the pore size and then particle size, morphology. So we can from here we can see how we make a plate or a nano or hexagonal plate of mesoporous silica. And then we also can tune it as a spherical nanoparticle and so on. And we also understand that mesoporous silica can be easily functionalized with many different type of either organic active molecules or any type of compound. So when I did my PhD, I mostly worked with the mesoporous silica, and then we functionalized the surface with either metal complex or something else, and then we do it for catalysis. But then On 2010, I moved to Europe, especially to Germany, and then to France, and then I work more to the interaction, more. We use the same materials, and then but we use it for the biomedical application. So in the beginning of my journey to utilize this mesoporous silica nanoparticle as a biomedical application, so I would like to understand first what kind of interaction between this our mesoporous silica with the living cell. So we functionalize our mesoporous silica nanoparticles in the outer surface with the different type of organic compound, such as amino, and then we also try to use the carboxylic acid, and then also RGD, and then also RGES. So and then we make a thin layer of functionalized mesoporous silica on top of a glass cover, and then we try to grow living cell on top of that. This one we use the HeLa cells. HeLa cells is a cancer cell derived from the human. And then we can see here that the glass covered with the silica nanoparticle functionalized with RGD, we could see the population of the HeLa cell grow really, really nicely. Also, as a comparison, we can see here the surface of the glass covered with the silica nanoparticle, which functionalized with the RGES. We barely see the number of the HeLa cells on top of that. So the A, B, and C, we did all in the same condition. So it means that the functionalization of the mesoporous silica play a very important role for the interaction with the living cell. And after that, we use the same mesoporous silica. We try to deliver to cells, especially in here is the glioblastoma cells. We deliver to the cell temozolomide together with the anti-mir 221 is a PNA type. And then why we use this combination between the temozolomide and this the PNA anti-mir 221 because we understand that the presence of the anti-mir 221 will enhance enhance the apoptosis of the glioblastoma cell. So in here we can see that combination between the temozolomide and the PNA give a very good impact to kill the cancer cell. So we understand this time also that we can functionalize further the mesoporous silica with the drug and also the anti-mir 221. So the next question is, after we understand that we can deliver or we can internalize this to the cell, the size of our mesoporous silica previously is around 100-150 nanometers. So what happened if we use a bit larger of particle? So we use a zeolite. Zeolite is aluminosilicate. In this case, we use the faugisite and lindatypial, with the size of around 1 micrometer. So can we deliver the micrometer size of a particle, silica nanoparticle? In this case, actually not completely silica, but aluminosilicate particle to the living cell. So in here we can see that we can put or we can internalize the zeolite after we put a tag in this case is with the dye, with the pyronin white dye to the cell, and we also try to understand for how long the the particle, in this case actually is 1 micrometer particle, enter to the cell. So by using the SEM technique, we understand that the particle will enter the cell after 1 hour. So before 1 hour, we still could not see the numbers of the particle can enter the cell. So also in this case, actually, I did not present in here, but we do a further study that most of our nanoparticle were internalized with the clathrin-mediated endocytosis. And again, now we already understand that our particle, how even 1 micrometer big size of the particle also can enter the cell. So the next question is, can we deliver it selectively toward a cancer cell? So and then we did a small experiment. We mix in the one culture media a healthy cell, in this case is EAHY92, with the cancer cell in the same media. So and then we use the same zeolite. In this case, it's a bit smaller size of a particle, is around 200-300 nanometers in size, and we modify this the zeolite with the cetuximab antibody, and then we colored our zeolite as red, and then we also colored or stained the healthy cell as green, and then also, but the cancer cell we have no staining at all. So if the zeolite selectively only enter the cancer cell, so there will be no overlap between green and red. But if the zeolite also enter the healthy cell, that means there will be an overlap between the red and green. So what happened in here? There is no overlap between green and red. It means that our nanoparticle, after modification, can enter selectively into A431 cells. So this is really good news for us that we can target a certain cell. So we move forward. We understand that even after for prolonged time, 1 week or something, so the particle, especially zeolite, is still inside of the cell. And then so we create a new type of material, silica-based material. Can we make silica nanomaterial which can break apart after entering the cell? So we can expect that there will be a clearance after delivering drug or any type of active molecule. So in here we design a silica nanoparticle which has a functionality that can break inside of the cell. And here is the kinetic study of the breakability, mimicking an international condition. This is the static condition. In the static condition, the particle will break apart in the 7 days. And then we also did some preliminary in vivo experiment that after 2 days there is no absence in the specific emission. It means all the particle we injected in the mice cleared out perfectly. So we also move further. We use the breakable material to deliver a big size of biomacromolecules. In this case, protein and if DNA and so on, and enzyme. So in this case, the SEM image of the particle is remain the same, as more or less around 50 to 60 nanometers. And in here is how the nanoparticle interact with the living cell. In the left side, you can see that after 7 minutes of incubation, the nanoparticle slowly enter to the cell, and then after 40 minutes, all of the nanoparticle we incubate together with the cells in here already under the cell membrane. And in the right side, this is just the blue one is the nuclei, and then but I think better you see in this one because here is much more clearly we can see that the nanoparticle entered and then into the cells and then stay there. So to prove that our breakable nanoparticle can really break inside of the cell, so we did some experiment by incubating the cell with our particle, and then we slice it and then put under the TEM under the TEM. So upper size of the picture of the TEM images is the non-breakable material, while the bottom part is this is the cells which we already incubate with our breakable nanoparticle. So after 48 hours, we can see clearly in the upper size that we can see the nanoparticle still there. However, in the bottom one, we can see after 24 hours, we already can see the deformation of the cell and the deformation of the nanoparticle. And then after 48 hours, it's clear that we could not find any particle, any silica nanoparticle inside of the cell. So it means that our breakable nanoparticle can really break apart inside of the cell and clear from the living cell. So now this finding we use it as a targeting and delivery, and also for control release. And currently, one startup company, a small startup company, Cbrix, is trying to commercialize this technology. And here, me with Prof. Len as a scientific board of this small startup company. Finally, I would like to acknowledge everybody who already helped me a lot with my research, especially my former supervisor, Professor Luisa Decola, and many other professor or postdoc or scientists who collaborate with me in the past year. Finally, thank you very much for your kind attention. Thank you.
Thank you so much, Dr. Eko. It's very interesting topic. So now let's move to our second speaker, Dr. Suresh Sagadevan. Is Dr. Suresh here? Okay, thank you, Dr. Suresh. Doctor, let me introduce. Sorry?
Dr. Suresh is still in the mute, so.
Oh, in the mute. Okay, let me introduce Dr. Suresh first. Dr. Suresh Sagadevan is a research scientist in Nanotechnology and Catalysis Research Center, University of Malaya. He is a senior researcher with specialty in nanofabrications, functional materials, and biosensor applications. Dr. Suresh has received many awards, including an award as the International Research Collaboration Recognition Award 2018 by Bangladesh University of Engineering and Technology and by National Defense University of Malaysia and or NDUM Malaysia. Dr. Suresh has published more than 250 research papers in the ICI top tier journals and Scopus Refer internationally, 12 international book series, and 15 book chapters. And today, Dr. Suresh will share with us his expertise and discuss with us about metal oxide nanostructures for catalytic applications. So, ladies and gentlemen, please welcome Dr. Suresh Sagadevan.
Thank you, Chairman. Can you hear me? Chairman,
yes.
Okay.
Yes,
okay.
Yeah, we can hear you clearly.
Yeah, I can share my slides. My folder is, how can I?
Can you share your
Yes.
presentations?
Uh, I face problem.
Okay, start share the screen.
Wait a minute.
Okay.
I'm not able to share my screen.
We already see your screen here. Maybe just open your PPT first, and then you click the Windows
Okay.
options. Yeah.
Can you see my PPT?
Yes.
Can you see?
Yes, we can see it. Maybe you just click the full
Stop.
screen options. Okay,
Okay.
yeah, that's great.
Clear?
Yes.
Okay. Uh, oh, sorry for this technical issue. Uh, I thank chairman for giving the nice introduction about me. First, I would like to thank the chairman of this conference, Professor Fatima, giving the opportunity. It's my great pleasure to give the talk about on metal oxide nanostructure for photocatalytic application in third international conference on chemistry, chemical processes, and engineering IC3PE 2020. I'm Dr. Suresh Agadevan, working as a research scientist in University of Malaya, Malaysia. I'm going to give a talk about on graphite carbonated with zinc oxide composite and graphene carbonated with cuprous oxide composite, and then two metal oxide nanostructures, cobalt oxide and nickel oxide. If time permit, I can present all the material. Uh, for the characterization of the composite, many different techniques are studied, like Fourier transform infraspectroscopy for the chemical functionality and bonding, and UV spectroscopy for the optical properties, and powder X-ray diffraction for the phase purity and crystal orientation, and FESM and TEM for the surface morphology of the prepared sample, and thermochromatic analysis for the thermal stability. So I can give the small introduction about these metal oxide nanostructures. Metal oxide nanostructures are great technological importance in environmental remediation and electronics because of their capability to generate charge carriers when stimulated with required amount of energy. The promising arrangement of electronic structures, light absorption properties, and charge transport characteristics of most of the metal oxide nanostructures has made possible its application as a photocatalyst. So especially much attention has been drawn towards the photocatalytic properties because of their application in environmental purification and decomposition of toxic and organic compounds. A major key requirement for improving the photocatalytic activity is to increase the specific surface area and enhance the crystallinity. This is very, very important for photocatalytic application. So these requirements are met by crystalline structure, nanostructure of this material. The several methods are used to prepare these metal oxide nanostructures, including hydrothermal, sol gel, chemical vapor, CVD, and sputtering are used to prepare this metal oxide nanoparticle. In this present study, we used for hydrothermal synthesis technique. So the next is the introduction about this my presentation. The current scenario, depletion of non-renewable energy resource and pollution. In the response to decreasing the supply of fossil fuels and the environmental problems caused by their explanation, the search for the renewable and the sustainable energy supply has been intensified in the past decades. So solar energy is clean, abundant, yet its utilization is still very low. So there is a strong need for scientists to develop sustainable and cost-effective manner for harvesting solar energy to satisfying the growing energy demand of the world with minimal environmental impact. So photocatalysis plays an important role for the conversion of solar energy into chemical fuel, electricity of the decomposition of organic pollutants, etc. All of these photocatalytic reactions occur on the surface of semiconductor. You can see here the photocatalyst needed for harvesting solar energy, high performance of nanomaterials, photocatalyst due to the increased surface area to volume ratio. So the first I'm going to present the fabrication of and for physical chemical characterization of graphene carbon nitride with zinc oxide composite with enhanced photocatalytic activity under the visible light. You can see here the first X-ray diffraction pattern of this composite graphene nitride with graphene carbon nitride with zinc oxide composite. You can see here the XRD pattern of A, B, C. A is represent the XRD pattern of graphite nitride, and B is can you hear me? Hello, Chairman, can you hear me?
Yes, we can
Yes,
hear you,
improve.
Dr. Suresh, but we cannot see your face because your
Oh,
video is off.
okay.
Can you like turn on your video, please?
Okay, sure. Yeah.
Okay, thank you. Sorry for
Okay.
the interruption. Thank
Okay,
you.
no problem. So you can see here that comparison of our X-ray diffraction pattern of graphene carbon nitride. The A figure, the A shows that XRD pattern of graphene carbon nitride. The plane is indicated by 002, and B is a XRD pattern of zinc oxide, and C is the composite XRD pattern. You can see here 110 and 101 plane is indicates this zinc oxide structure, oxide structure, and A is 002 plane indicates the graphene carbon nitride, and C is clearly indicate that 002 plane is present in this composite. So it is clearly stated that zinc oxide incorporated with this graphene carbon nitride. So which is confirmed by this X-ray diffraction. And then FTR analysis, once again we confirmed that carbon nitride consisting of vibrations peaks around at 1242 and 1320 and 1403 centimeter can be linked to the aromatic of CN stretching. And the band at 820 centimeter inverse 1 due to the outer plane. So the CN stretching, which is also clearly state that the graphene nitride is present in this composite. And also we could confirm that the zinc oxide bonding, zinc with the oxygen bonding, which is occurred at that 522 centimeter inverse 1. So also the presence of wide band. You can see here this wide band indicated that OH stretching of vibration from absorbed by the water or moistures. And next, the optical properties. You can see here the optical properties of graphene carbon nitride and composite, and also zinc oxide. The maximum absorptions observed for three materials, the maximum of 389 nanometer for the zinc oxide, and second one is B. The black one is B, is 1471 nanometer for composite, and then the next one is the last one, that one is C. C is a green, which shows the 4 nanometer. And corresponding, you see that the next one is the band gap values. Also, we calculated using the tau flat. The band gap value is calculated for zinc oxide is a 3.06 electron volt, and then composite material B. You can see here this is the band gap values of B is 2.47, and graphene nitride is 2.35 electron volt. And surface morphology characterization, you can see that really clearly you can understand that this is a graphite carbon nitride, which is a sheet-like morphology. You can see here, and then this one is a hexagonal and cylindrical shape of zinc oxide surface morphology, the figure B. And C shows that both is there. You can see that this is a composite surface morphology. You can see here the shades-like morphology is incorporated with the cylindrical and hexagonal shape of this zinc oxide nanoparticle incorporated with this composite. So which is clearly stated that once again we confirm that this is a composite, successfully formation of this composite. And also we did for that AFM analysis. You can see that A figure represented by this surface morphology of topographic image of graphene sheet. You can see here, this is a graphene carbon nitride, which shows a sheet-like morphology. And B is, which is confirmed that it is like a rod-like structure of zinc oxide. And C figure, which is also again, once again confirmed the formation of the composite. You can see here, both are present, sheet and rod-like structure. And thermal characterization, you can see that the pre-sample decomposed at 180 degrees Celsius, the minimum of weightless occurring at the pre-sample, and is attributed to these loss of hydroxy groups and water moiety. So in the case of zinc oxide, the significant weight loss occurred at the region of 550 degrees Celsius, and this can be due to that phase changes occurring in this prepared of zinc oxide sample. And also, you can see that other sample of graphene carbon nitride, this is red color. You can see that the weight loss is attained around the temperature of 450 degrees Celsius, which confirms that phase change of melamine to graphene carbon nitride. Yeah, you can see this very interesting of photocatalytic studies of carbon graphene nitride zinc oxide, that UV light is illuminated with the time period of 0 to 45 minutes. You can see here A and B and C and D we use for different dyes. One is a malachite green, and B is a rotamine B, and C is a Congo red, and D is a red ink solution. You can see here from the figure the different solutions, MG, RHD, and Congo red dyes and RA solutions. Over the different time of period, you can see here in the table 0, 5, 10, 15, 20, 25, 30, and 40. There has been some significant photocatalytic activity observed for the graphene composite, graphene carbon nitride with zinc oxide composite, and the respective efficiencies are also tabulated here. From the analysis, we can observe that the composite has activity against all the dyes, and solution tested this activity getting reduced within this increase of in the period of time. You can see here, and this can be due to the loss of occurring in the number of active catalytic sites. Also, among all the reactant tested, we observed that the higher observation, you can see here this RA solution. RA means red ink solution. You can see here. This is represented by a D figure, 602 nanometer. This is the efficiency. You can see although table the time with respect of a different solution, the RA solution only shows the highest value 0.9654. And photocatalytic degradation efficiency with respect of irradiation of time, you can see here. From this graph, you can confirm that the malachite in green shows at higher efficiency. It is showing for 97.24%, which is compared to that red ink solution. Red ink solution is confirmed that 46.99%. So, which means that you can, it is observed the photogradation of all the tested dyes and solutions extremely slow in the absence of catalyst under the visible light illumination. So we observed that the significant change in the degradation of organic dyes like MG, RHB, and Conco red dyes and RA solution, that by indicating the role of the photocatalytic towards the dye degradation process. So which is confirmed that the figure, the degradation with irradiation of time. And then we can go for kinetic studies of different solutions, red link and Congo red, rotamine B, and malachite in green. You can see we found to be that R squared value of that is a slope value. You can see which one is higher. Red link is 0.5301, and Congo red is 0.2995, and then rotamine B 0.1763, and then the last one is malachite in green 0.0276. So therefore, in the present work, we have tested the photocatalytic efficiency, the stable of graphene carbon nitride with the zinc oxide composite in the presence of UV light by taking advantage of this water splitting and reaction against many different carbon nitrides. So we observed that analysis of, you can see that this is also the kinetic studies. So the the schematic representation, you can see here the schematic representation of this detailed mechanism of for this involvement of various oxidation and reduction pathways of the surface of the photocatalytic shown in the figure. You can see here, this is conduction band and valency band. For the observation of such photocatalytic activity under the UV light, we hypothesize that some of the electron in the conduction band of the composite gets readily captured by these absorbed O2, which is greater than superoxide radicals. So next, I am going to present fabrication of graphite carbon nitride cuprous oxide composite and its enhanced photocatalytic activity for organic proteins degradation. You can see here, this is experiment setup. We prepared that composite by hydrothermal method. Okay. Yeah, you can see that structure XRD pattern of this composite. You can see here, this is a 110 that red indicated that 110 and 11 plane and 200 plane and 220 plane indicates that which is confirmed that cuprous oxide present in that composite. And G carbon graphene carbon nitride, which is confirmed by the plane of 100 and then 002 plane. So which is the highly crystalline nature of this XRD pattern, which is confirmed that the material have that, the composite have that highly crystalline nature. And then FTR XRD.
Dr. Suresh, please remind me. Let me remind you that you only have 1 minute.
Oh, okay. These are all FTR analysis, which is also confirmed that. Okay, these are all optical properties. Yeah, this is very good, interesting. You can see that these first figures A and B shows that graphene carbon nitride, the surface morphology, you can see the sheet-like morphology, and then this one is octahedral shape of cuprous oxide, and then the third is, you can see that image E and F, that this is octahedron is randomly distributed in that graphene sheet. So which is also confirmed that successful formation of this graphene carbonated with cuprous oxide. So I prepared the more slides, but due to the time constraints, I could not explain it, but I can show you these are all photocatalytic effect I did, and cobalt oxide nanostructure material we done, and we published in recently we published this work in that we used for crystal violet and metal violet, and then nickel oxide also we performed that. Okay, thank you for giving the opportunity to share my experience in this particular topic on metal oxide for photocatalytic activities. I thank for all my collaborators who supported my research career. Without support, I cannot publish any papers. So once again, I thank for Professor Fatima and other committee members and other chairman for the nice introduction about me. Thank you.
Thank you, Dr. Suresh. Really sorry that we really have a tight schedule for today, so I have to like cut your presentation. Really sorry about that. Okay.
15 minutes, yeah, 15 minutes not able to present full work. Okay, I cannot explain many things. That is a problem.
Yeah, maybe you can share the presentations with the committee, so yeah, people can read your work really really nicely. Okay, we only have like 5 minutes to answering questions sessions. If the participant have any questions for both speaker, you can raise your hands or and ask the questions directly for the Dr. Eko and Dr. Suresh. No questions from the participant. Okay, I have one for Dr. Eko and one for Dr. Suresh. Okay, Dr. Eko, I have read that like one of this advantage from using mesoporous silica nanoparticles is the scattering size distribution is not really good. Is there any like preparation technique that can reduce or can solve this particular problems?
Thank you for this question. Yes, actually we have kind of trick. We usually we never use a synthesized material to use it directly to the application. So if you in the organic chemistry usually use the purification method, so we also use the same. So we purify it with several techniques such as gravitation or this centrifugation. I mean, we use several time centrifugation, and then to obtain this the more homogeneous particle size.
Okay, so it's more than focusing on the purifications process to get the really nice size distributions of mesoporous silicon nanoparticles. Okay, thank you so much. And for Dr. Suresh, one questions.
Yes,
Is
yes.
there any like really I mean the really the advantage by using the silicon nanoparticles
Yes,
for the photocatalytic
yes,
process,
yes.
because I think more researchers now tend to use the like a bio compounds for photocatalytic process. Can you like explain what's the most abundant advantage from the silicon nanoparticles?
Yes, yes, very
Sorry,
good.
from sorry.
Yeah, very good question. Actually, metal oxide play the vital role for the photocatalytic application, especially for tin oxide and then titanium dioxide. Many material, well-known material for zinc oxide. Zinc oxide is played the vital role in that photocatalytic application. So we tried with that graphene composite. So when you go for with any graphene sheet, so it is again enhance that photocatalytic properties, so that we can use the incorporated with graphene carbon nitride with many metal oxide like tin oxide, copper oxide, zinc oxide, and then silica oxide also we are trying. So if we go for with any composite material which is show enhance that properties more than the single compound. Yeah.
Okay. Okay, thank you so much for the answer, Dr.
Thank you.
Eko and Dr. Suresh.
Thank you.
Okay,
Thank you.
so
Thank you,
this
everybody.
is this is the end of our sessions. And before we close these inviting speaker sessions, I would like to ask for to everybody to join for the photo sessions. So please turn on your video so I can see your beautiful and handsome faces together, and we can take the nice pictures for our sessions in room D.
Is it okay?
Yes. Okay. Can everybody give a really big smile? Okay, I'm gonna count 1, 2, 3. Just hold your smile. Okay. 1, 2, 3. Smile, please. Okay, one more. Okay, we wait for Dr. Suwari and Jelita. Okay, sorry, we need to wait for more participants. Just wait, please. Okay, one more take for photo sessions. Okay, 1, 2, 3, smile. Okay, thank you so much, everybody, for a really nice sessions here. I would like to say thanks again to the presenter for these sessions, for informative and interesting talk, and the audience for still join the sessions for in room D. Hopefully the presentations will be beneficial for everybody, and thank you for attention. And after this, we shall return to the room, the meeting room from the IC3PE International Conference. Thank you, everybody, and see you in the future. Thank you.
Thank you.
Thank you very much. Thank you, everybody.
Everybody take care and be safe. The pandemic situation.
Okay. Thank you, Dr. Suresh.
Hello. Hello. No, who is speaking?
Sorry. We will get to the next event is seasoning to certificate appreciation. Certificate fall to Dr. Suresh Sagudevan as speaker, and then certificate appreciation to Dr. Eko Adi Pasjanto, and then certificate appreciation to Mrs. Sri Agustina PhD. Lastly, as the host, I would like to thank you to speakers, moderator, and all participants of the invited session that has been completed. Next, we will return to the main room by live room. Let's close this event with hamdalah. Wassalamualaikum warahmatullahi wabarakatuh. Silakan Bapak Ibu bisa live room untuk kembali ke room utama untuk proses closing.